Hell yeah. So we're going to go over Hooke's law for plane stress. And I don't think I've ever gone over this. I don't remember this from college. I'm sure I had to do it, but for whatever reason I was able to pass. And I even took this class twice. Well, I can't even say that because I failed out after the first test. So I didn't get very far the first go around. And then the teacher for this, the second go around, was just a lot easier. And so hell yeah. But it made me appreciate mechanics of materials. That's what we have. We have James M. Gear. And so that's what we're going to go over. And so, hell yeah. It's about 10 o'clock at night, and I just woke up a couple hours ago, and there's no coffee shops open. This is what I would do at a coffee shop, you know what I mean? I would put my nose to the grindstone and do this. You know what I mean? I would not do this tonight. I would just space out. So we're going to try to chisel my way through. Okay, hell yeah. And so this video is not going to be that good, you know what I mean? And it might be a video that just shows someone learning, you know what I mean? I haven't read this stuff, so I can't read it and teach you. But I'm just going to read it and see if I can teach myself through. And in the meantime, you can kind of see how that process would go. The hardest thing about textbooks, I'll read one sentence and just space out. And so, hell yeah. So what leads us up to this was the previous videos that I've made on Moore's circle is saying, hey, we're given an element, and maybe this is oriented at 0 degrees, meaning that we have some sort of beam, and we took a little chunk out of it, and we put it in the normal just x, y, z out of the page axes. And we found the numbers on the tension and compression, and the tension and compression on the side and top faces, as well as the shear pressures, the shear stresses. I don't know why I dislike the word stress so much, but anyway, I guess normal stresses and shear stresses. So we're going to know all three of these values. And with the Moore circle, we can rotate this element and find out that these values might increase. You might find a maximum of one of these normal stresses at some sort of inclined element. You know what I mean? Had we just chopped the element at that angle, we have our beam, and let's just chop an element like this. We're going to use free body forces. You know what I mean? Knowing that we'll know the you actually use free body forces first. You know what I mean? Because we know that not quite. You can if you have if these two lines were just a bar and then I chopped it at a 45-degree angle. Well, hell yeah. Then I'm opening up a face, and then the forces along these face and the normal and shear have to match the tension that I'm putting on it. But I guess a more detailed approach would be, what am I getting at? Well, on that face you'd have, I don't know, man. I think I was going, I still get confused of chopping a tiny little element. Because if you chop a tiny little element, you can't use the entire force. So it's just kind of fascinating that I can chop through a huge element and find the forces needed to balance that face. And then what happens, though, is you're just going to say, okay, those are the normal forces and shear forces on that face. And so that's where some of the previous chapters in bending stress, if you have a shear force on a face, like at a 45-degree cut, the shear force isn't going to be uniformly distributed because you can't have any shear force at the ends on the free surfaces. Because if I identify, let's say this is actually a force vector, if I identify a force right here, and let's say this element was on the very top surface of a beam. If I identify a force vector up on this face, I need an equal and opposite one down on that face. That's Newton's laws in the y direction. Some of the forces in the y direction are 0. That's going to induce a torque or a moment or a couple that's going to turn this object this way, which has to be resisted by some sort of force. You know what I mean? So this force could resist it, and if I did have this force, well then I'm unbalanced in the x direction. This thing's going to travel this way. And so the sum of the forces in the x direction have to be equal. And then so I'm going to have this force up here. But on a free surface, that force doesn't exist. So that's kind of what happens. And then sure, if you cut down into this beam a little bit, well, hell yeah, then I can have some shear force here and shear force here. But if it doesn't exist at the very surface, then due to continuity, it's gonna, if I just go down just a little bit, well, there's still gonna be hardly any shear force here, hardly any here. So yeah, these will be hardly any because it'll be approaching zero as it meets that that face. Okay, so why did we do that? Yeah, that was just to explain how if we take a cut, and that's what I need to do more of. It's just like if I have a beam, well, let's take a bunch of cuts. One in the center where the shear stress might be max, and then one on the surface where we're going to have no shear stress, and then somewhere in between. And they do that. There's a kind of one place in this book that they do that. I just think that's yeah, I guess that's just shame on me for like not knowing exactly all, like not going through those problems enough to have that totally settled in. Where I still, for biaxial stress, if this is a bar and I'm yanking on it, I can really just cut at any angle, and then whatever this surface is, I can just say, hey, we have a normal force and a shear force, and that shear force is just going to be the average, over that surface. But if I say that's the shear force over that surface, then I'm getting an average shear. I'm getting an average shear stress. So doing it that way, if I had biaxial stress and I'm cutting at a 45 on this surface, I'm getting an average shear stress if I calculate it that way. But that shear stress is going to be actually zero at the very ends, and it's going to be a maximum in the middle. So yeah, so that tripped me up actually 3 weeks ago when someone gave me a problem and it involved average shear stress, and especially with textbooks, there's literally no stone unturned, and so everything has a meaning. And that's kind of also the downside of textbooks, because if it's really difficult to read if you didn't know even what this Y meant. I mean, maybe you could figure out, okay, this Y means maybe this direction, this X, maybe synonymous with this direction. But what's this? XY, you know what I mean? And so and that's somewhere in the book, you know what I mean? This shear force, and I'll just call it a force all the time. I get better at that. This shear stress, because it's in units of force per length squared, force per area, PSI, or pascals, newtons per meter squared. That's the units on shear stress. All right, so this shear stress is on a face, and this face is in the positive x direction, and this shear stress is in the direction of the positive y direction. And so that's what we call a positive shear stress. If this, and then over here, this one's on the negative x face, but it's in the negative direction. Those negatives negate, and this is associated with a positive shear stress. Cool. And then positive y face, positive x direction, positive shear stress. Negative y face, negative x direction, negative and negative becomes a positive shear stress. All right, hell yeah, that was brutal. So that was at least an introduction where we kind of go over something and we learn something. The kicker on stress, or just prior to this chapter, was like, hey, we're given these three values, and one of these values might get bigger. You know what I mean? My normal stress might be twice, and my shear stress might be non-existent in this given state, and then it's actually pretty big. And so that's kind of what we're interested in. And once we get those numbers and find those bigger maximum numbers, then we can compare them to the material and see if, because the material can only handle so much tension, compression, and shear. And so we say it can only handle so much compressive stress, tensile stress, and shear stress. And so there's going to be a number for each of those given a material. Steel is going to be equally strong in tension and compression, but the number will be half for this shear stress, for the PSI and shear. So given that, I thought that was a good way to go forward in this section. Let me drink some water. Was to look at, because what we're going to be doing is, I think I even picked the wrong chapter, 569. Oh, 7.5. More circle. And then I chose to get to, Hooke's law for plane stress. Yeah, I even chose the wrong section. No, we're good. So Hooke's law for plane stress. How's this going to get us into to strain? I thought we were doing the strain. Hooke's law for plane stress. And so we do have this strain. Are they relating strain to stress? And then so here's normal strain, where you just have a change in length in kind of a cardinal direction. This is going to be shear strain, where you have a rotation of the element. And you're going to have an equal rotation from both faces. These sides of this element won't change. And so you'll either get a diamond shape in this first quadrant to get kind of peakier, or negative shear strain is this is going to become a squat diamond, and the edges will protrude into the second and fourth quadrant. Okay, hell yeah. And so, so we are going to be working, that's the whole idea. I just wanted to go through this because I do not like the term strain, but I was just going to say is that it's the same as stress. Each material can only take a certain value, certain number for the strain. It can only change length so much before we have failure or issues, or it becomes yielded. Like right here, that's the strain in the Y. I thought that was the yield strain or something. Anyway, so so this value for the material can only be so much, you know what I mean? And once we exceed that value, we know we have issues, and we can redesign our whatever we're designing. So triaxial stress. I really, and then that almost plane, and then we get to plane strain. So why do we have these preliminary chapters? I guess that's where we're going to go over. So this is brutal. This is why I don't want to do this. You know what I mean? Because even just right off the bat, I feel like I don't know what's going on. All right, so let's read our way through. So we have the stresses acting on inclined planes. Okay, that's when we rotate this thing, so they're probably going to be bigger, or smaller, or whatever, when the material is subject to plane stress. Now, plane stress means that we only have stress in the x, y, and then the shear is all about the x, y. So even there, this word plane, sometimes I might just not pay attention to it at all. But yeah, we're only focused in the x, y rotation. And Hooke's law for plane stress. Oh, so this is why I'm getting confused, because stress can be stress and strain are two different things. So yeah, I'm still confused of why they're calling this section stress and why we're introducing the term strain. I guess let's read on. But yeah, that is good to throw your first questions on the board. Be like, what? Anyway, so stresses acting on inclined planes when the material is subject to plane stress were discussed in the previous sections. Section 7.2, 7.3, and 7.4. We're in section 7.5. The stress transformation equations derived in those discussions were obtained solely from equilibrium. Okay, so yeah, the equations given any chopped up angle were from equilibrium. We had a force on one side, and then if we have an angled face, it can only have a normal and a shear, and then so we get values for those. They're going to be over a different area after the cut, and so so now I get it. So if you had something, let's say this was our rod, and you're pulling on it this way and you're pulling on it that way. What we can say is that over this whole face, if this whole face was normal in this direction, we could find the normal stress. Same thing on this face. So I can find any cut that's vertical, I would be able to find the normal stress, the number for that. And so hence we can, the easiest orientation for our cube. So if I made this cube, it wouldn't matter in that regard. It wouldn't matter if my cube was at my little cube was at the very top of that, or the very bottom, or in the middle, or anywhere else in between. The pressure on this stress due to normal stress, the stress on this face, which is in pressure, units of pressure, will be the same no matter where I orient that object. And cool. Yeah, I guess you still have to throw an asterisk on the shear stress, because if you take the cut here or in the middle or down here or somewhere in between, this shear stress is for sure going to vary. Check this out though. But if we just have biaxial forces, we do not on a cut like this stress will. Yeah, so let's do that. So we have a force over here on this bar. We cut it perfectly perpendicular. We know we're going to have stresses that are associated with forces. So we're going to have a normal force and a shear force. But because this is perfectly horizontal, we won't have any shear force. Hence no shear force. Hence if we have biaxial stress, this will be 0. Okay, hell yeah. So then this term would be 0 at any location when we just take the simplest thing of just pulling on something on both ends. And then after that, so we can have our element. So now we know what the element would look like at any place on the cross section. Cool. We still have to pick a place on the cross section to take our element, but at least this is 0. It won't have any, it'll just have tensile stress. So it'll just have normal stress in the positive x direction right here. This will be 0. And then the game begins. We're going to take our element, and these stresses, this would be a stress diagram, but is associated with a force diagram. So if I get down to this element, I can put this element down here and make a force diagram. This stress operates on this little chunk of area, and then that's going to be a force in that direction. And we're going to have a force equal on the other direction. There's no shear stresses. There's no stresses in the y, normal stresses in the y. So when we incline our plane, that's when we start to slice through our cut, and then that is going to open up. We're going to have a force this way. On a cut, you can only have a normal force and a shear force. That's resisting. And I guess that's a better way to say that is if we open up this cut, we have to have a force still in this direction. So if this is pulling this way and we make a cut like that, we have to have a force on that surface that's in this direction. And that is associated with like this direction, in relationship to that angled cut, is going to have a normal component and a shear component to actually get to that vector, to meet that equilibrium. And so hell yeah, then you introduce a shear when you angle this this cube. So biaxial stress, two tensions. With a 0 rotation, you're just going to have normal stress. But when we rotate this, then you get shear stress, and that's going to become maximum at 45. Okay, hell yeah. So that's kind of what these sections were all about. Still everything, these three numbers are the only numbers. We don't have any shear in this. On this face, you can only have a normal direction. You can't have a positive arrow and a negative arrow at the same time. Free body diagram would say, hey, that those two stresses opposing would be associated with two forces, and those forces would add like vectors, and you'd have a resultant force, and it would either be net positive or net negative, and then that would be the resulting force with that area, so you'd have a resulting stress due to that. Now, when it comes to shear stress, you can have this is a stress with this arrow in this direction. It's on the positive x face, and it's in the y direction. You could also have a stress that's on the positive x face in the positive z direction. So this face could have two different arrows for shear, and every face could. You could have a normal and two arrows for shear. Normal and two arrows for shear. And even this face, we don't even have a normal force on it, but this face could have a normal and then two arrows for the direction of the shear forces. And so again, we're talking about plane stress, so we're not interested in any stresses along this face, and we're not interested in any shear stresses that are on this face but in the z direction. Cool. All right, so now I think I can move on. Now in this section, we will investigate the strains. That's what I thought. I just didn't. There should be parentheses here. Strain. And we want to do that in the material. And I want to get this done in 3 hours. But anyway, so which means that the material properties must be considered. However, we will limit our discussion to materials that meet two important considerations. First, the material is just uniform throughout, and it's kind of fascinating reading these. I kind of know what they're going to talk about. It's uniform throughout, and when we tug on it just a little bit, it's linearly elastic, follows Hooke's law. So let's read this. The material is uniform throughout the body and has the same properties in all directions. It's homogeneous. It's also, the material is isotropic, which means it's not tapered. So it's you got a beam, it's the same cross-sectional area all the way across the beam. And second, the material follows Hooke's law. Linearly elastic material. And this works great for us because if we get numbers that are bigger in stress or strain, that means that it's no longer linear elastic, and at that point, those are usually your failure points. Like, thank God in material mechanics, you don't have like, oh, it's going to be linear for a quarter of its strength, but most of its strength is in some bizarre, unlinear way. The cool thing about material mechanics is if you stay within that linear range for that material, hell yeah, everyone is safe and sound. And we can design pretty much everything to be in that linear range. And that's why these equations, a bit hellish, are still come from, pretty solid and basic adding, subtracting, not anything empirical. Okay, sweet. So under these conditions, we can readily obtain the relationships between stress and strains in the body. Let us begin by considering normal strains. So strains, I just like to change this word to change in length. I like to change it to stretch. Stress is strength in PSI. Strain is stretch. There's going to be a change in length. And just like stress, that's why I'll catch myself saying shear force, even though I shouldn't do that. But the shear stress is associated with a shear force because this stress is on this area, and so it's you could do a free body diagram with a shear force. Same thing with this normal stress. It's associated with a force, a normal force. And so because of that, and then when it gets down to materials, is if I had a 1-inch bar of steel, I can pull 58,000 pounds in tension on it. But if I only had a half-inch bar or a bar with a cross-sectional area of a half an inch. Like maybe it was 1 inch by half an inch. That was its sectional area. I could only pull in tension on that 29,000 pounds, or half. And so, but the pressure that is on the surface is the same. Still, at 58,000 pounds of psi in normal tensile stress, that is going to be a failure point for steel. So the same analogy is going to be used for strain. Is that steel? If I had a 1 meter bar of steel, that's going to be 1,000 millimeters. I can only lengthen that bar of steel by 2 millimeters. And this value, but if I had 2 meters of steel, 2,000 millimeters, I could lengthen that just fine up to 4 millimeters, and and so on. If I only had a half a meter, 500 millimeters of steel, I could only lengthen it 1 millimeter. And so we have this proportion. I can only lengthen, and you could think of that as a percent. If I had 1,000 and I can increase it to 1,002, then that was a percent increase of 0.2%. Except that those numbers are just so small, it's just really hard to wrap your mind around the percent increase at 0.2%. Like, I have a hard time of, 0.2%, does that make sense? Not really. But the proportion, is probably even worse, because you're taking 1,000 and multiplying it by 0.002 to get 2. You know what I mean? And so, but any length multiplied by 0.002 for steel is going to give you the max change in length. So and even in this textbook, anytime they use the term strain, they should at least define what strain is. Strain in the x direction is a change in length in the x direction divided by the original length in the x direction. So if I had like strain for steel is 0.002, so let's talk about where that number comes from. That's going to be 2 millimeters divided by 1,000 millimeters. We said that steel bar could lengthen a change in length of 2 millimeters. Its original length was 1,000. So this value on strain, and that's going to be a max strain, is 2 divided by 1,000, or 0.002. Just like up here, if we had a 1-inch steel bar, we could put a max pressure in the normal direction. We could have a normal stress up to 58,000. But let's say we're just pulling half that on that same area. Well, this number, our given number, is going to be half. And so, but for what we're doing in this chapter is like, we found these numbers like fairly easily, because this is just the unrotated direction. And we can find all three of these numbers. And then what we want to do is rotate this element, and we know that these numbers are going to change and maybe get bigger and have maximums. And then we want to compare that maximum to the strength of the material. So we're going to do the same thing for strain. So let's say I'm pulling on this steel bar that's 1 meter long, and we're pulling 29,000 pounds. I would expect in this direction, this x direction, my strain to be half of max. We just said max was 0.002. That's the hardest part about strain, is like you're dealing with small numbers that don't really have meanings. And especially, it's a ratio. The units, people would call it unitless. I think that's a bad idea. It's a ratio of units. It's a change in length divided by length. So, because it's a change in length divided by length, if I took strain and multiplied by length, then, I would get the units of change in length. And so, and if I inverted this, because this is change in length divided by length, if I invert it, it would be length divided by change in length. So if I took inversion of strain times change in length, well, that would give me the length of something. Cool. I mean, yeah, let's say you just had like a train tunnel with a steel bar, or like in a cave, like in a mining, like a mine shaft or something that was like horizontal, and you had a steel bar, and you were going to tension it, and then as you're tensioning it, you changed its length, and you knew the material was. Would this work out? Could you figure out? No. You'd have to know the strain. That second part of inverting, I don't think that would work out. But anyway, so strain is going to be a change in length divided by the initial length. So even this value for strain EX is going to be equal to the change in length right here, which they're just calling AEX. So if I knew the strain, because strain is the change in length compared to the original length. So yeah, even just the way they've written it. So let's say this is the quantity for change in length. Okay, the original length is A, and so strain is this change in length divided by A. The A's cancel and you get strain. Cool. So that's just, you know what I mean? It seems like a like redundant. But anyway, so that's how we have this labeled. And if you just put change in length here in the X direction, then your strain would be your change in length divided by A. Cool. And I guess what they're doing, if I had a stylus, so this strain is change in length. If this was change in length, strain is this change in length divided by A. So we would have strain is the change in length divided by A. And if I wanted to solve for change in length, I would bring the A upstairs and say this change in length is just A times the strain. So sweet. So that's what they did there. So that's kind of the first and hardest parts about textbook, is just like, well, where are they getting, you know what I mean, this little value? And I think it's worthwhile to kind of play around with it. It's just usually a little bit of algebra. You know, it's taking the known equation and then just kind of manipulating. And I've talked about that before. If we have this equation that says strain is change in length divided by length, then we got three things in equation. You can rearrange that equation three different ways. All right, hell yeah. And for just our generic stresses, we're going to be pulling in the X and pulling in the Y. So therefore, we're going to get changes in the X direction, changes in the Y direction. Now it seems like we might not get changes in the Z direction, but Poisson's ratio says that if we pull on something axially, it's going to lengthen in this direction for sure, but it's also going to squeeze in on the other four surfaces. And so any normal stress in the axial directions X and Y, we will generate a strain, a change in this length in this direction. So the way they have this is going to be a positive change in length in the Z. That might be associated with a compression in the X, and a compression in the Y would cause a positive change in length. All right, hell yeah. So that was that sentence. Let's read on. Now, again, I have to be doing this more for me, you know what I mean? But it's good to, like, go over the things that I know that I can teach. I mean, but basically, sometimes the goal is to read a textbook to try to find the things that you don't know and see if you can know them. So the effects of these strains are pictured in this figure 725. This is an element of material subject to the normal strains in the X, Y, and Z direction. And again, strains can be thought of as changes in length. stretching in those directions, which shows the changes in dimensions of a small element having edges of lengths A. So this length is A, B, and C, respectively. All three strains are shown positive elongation in the figure. The strains can be expressed in terms of stresses by superimposing the effects of the individual stresses. So that's the part that I was kind of waiting for. It's like, So if I do know the strain, that's why I do not like the word stress and strain. They sound almost the same. If I know this change in length in the x, I know that has to be associated with some sort of stress in the x. If this was 1 meter long, and then this change in length was 0.2 millimeters, booyah! I know the stress on this face, the normal stress is going to be 58,000 pounds. So it is good to pick a material. I picked steel, and I pick a 1 inch, because U.S. customary works good for me, and so I know that it can take 58,000 pounds. And then, but for length, you know what I mean? Because let's say a thousandth, 2/1000ths of an inch means nothing to me. You know what I mean? Because if I was using PSI, the base unit is the length unit is inches, and 1 inch of material won't even have a visible change in length. So that's where I kind of combined a 1 inch by 1 inch cross section of steel, and I can understand that the pressure on it is 58,000. And then I use metric to say that chunk of steel is 1 meter long, 1,000 millimeters, and the max change in length it can have is 2 millimeters. And so because strain is dimensionless, there's no harm in just kind of switching up to meters and millimeters. Okay, so hell yeah. So if I did see a change in length, if this was 1 meter, 1,000 millimeters, and we had a change in length in the x direction of 2 millimeters, that's going to be a strain. Strain is the equation change in length divided by original length. So it's going to be a strain of 0.002 because we're having 2 divided by 1,000. Hell yeah, so now we're on board. And that strain is associated with, that's a max strain. That's the maximum number we can have for this material. So that is totally synonymous and linear with the maximum stress. And that's where Poisson's, that's where they're probably going to talk about, this modulus of elasticity is just a way to say, if I have 2 apples, I can make 1 apple pie. If I have 4 apples, I can make 2 apple pies. In this case, if I have 0.002 of strain, I have 58,000 pounds of stress. You know what I mean? And so that's just the bummer of material mechanics. You're relating something really small and then to something pretty substantial. 58,000, I think we can, that's the weight of a half-loaded semi. You know what I mean? So at least that has, but any numbers that are less than a tenth, I think is difficult to kind of wrap your mind around. Anyway, so we got that strain is very small. And how do we relate 0.002 with 58,000? Well, the equation to relate them is that this 58,000 is equal to, so it would be y is equal to mx. That would be the equation of a line, or 58,000 is equal to 29 million times 0.002. 29 times 2 is 58, and then 29 million times 0.002 gets the job done, and we get 58,000. So E for steel is 29 million in U.S. customary units, and that's how we're relating strain and stress. You're just basically saying 58,000 is synonymous with 0.002. That means 29,000 psi is synonymous with 1 millimeter, or 0.001 strain. You know what I mean? 1 millimeter per 1,000. And so, hell yeah. So it is good to just kind of have a material where it's max, and then it's going to be kind of way easier to kind of see that linear relationship. Cool. So So probably right here is where they're going to say, and I wish they even just, so what did I say? I said that stress was equal to this modulus of elasticity, which is just a constant that makes the linear equation. It's the slope of the linear equation. You know what I mean? Because the line for it goes through the zero axes. Because if you have zero stress, there's zero strain. If you put zero axial force on a chunk of steel, it's going to move zero. It's going to stretch zero. And cool. So, and we have that 29 million to relate a small number to a fairly substantial number. So if stress is equal to 29 million times strain, or if stress is equal to E times strain, then E is stress divided by strain. So here we go. So here's where we got that stress divided by strain, and we're going to, like right now, I don't know why it's this minus that. But what we did say is we have Poisson's ratio, so we are going to take that into consideration. Oh, and we're in plane stress, so there's only two terms here, so I guess I kind of figured out that, is that we don't have any tension or compression in this y direction. So we're not going to get a Poisson's effect. If we did have a tension in this we don't have anything going on in this z direction. If I did pull on both sides in the z direction, this length is going to decrease. We don't have that. But what this negative is going to be is like, hey, we want to consider all stresses in the positive direction. So if I have a normal stress in the axial y direction, that's gonna make it pull in the y direction, but it's going to make it suck in the x direction. It's only going to suck in a third. So you are, like, if you have tension in one direction, like the material is going to expand. Its volume is going to change positive. But it's going to suck in on all four of these faces, but it's only going to do so amount that's 30%. And I guess I never thought of it as the fact that it's going to suck in 30% on this face and 30% on this face. So let's talk about that. If we're pulling axially in the y direction, and this is 1,000 millimeters, and I'm able to actually, and let's say I'm able to pull it just 1 millimeter. Let's talk reasonable things that we can do with steel. Is that this distance increased by 1 millimeter? It means that this distance sideways decreased by 0.3 millimeters. And then also this distance right here decreased by 0.3 millimeters. So because it decreases on both sides, the net change in volume is going to be kind of closer to the original. But anyway, so let's talk about how they derive this, and maybe let's just start reading through it and then trying to compare it. So it says, for instance, the strain, and you call this epsilon. That's the first time I've said that. So we have strain is epsilon x, and this is just strain in the x direction. That's probably how I would call it. But epsilon x in the x direction due to the stress sigma x, and normal stress in the x direction. Oof, sorry, I'm getting too wrapped up in just saying these things. So, for instance, the strain in the x direction due to the stress in the x direction is equal to the stress divided by E. Yeah, and so why is that? It says the strain in the x direction is due to the stress in the x direction. Because we said stress, 58,000 psi is equal to 29 million times 0.002 strain. And so stress is equal to this thing that relates stress and strain, E, times the stress. So we have stress is equal to E, which relates them, to the strain. Sorry, I keep messing up the strain. So stress is equal to a constant times the strain. And so that means, and what are they? So they're saying that the strain is equal to the stress divided by that constant. The strain is equal to the stress divided by that constant. Cool. So now we're up to speed on that. and that's strain. Strain. So if I knew the stress, and that's what we're given. Like previous to this, these sections, we were given initial stresses, and now I can say that the strain in the x direction is associated with this stress divided by the material property, modulus of elasticity, the thing that relates stress and strain. If my stress was 58,000 for steel, I would expect a strain of 0.002. So you can always use that to kind of check your numbers and stuff like that. And so where E is the modulus of elasticity. Also, and I think they do such a disservice, because I always just said, cool, it's a modulus of elasticity. I don't know what the hell this even means, when it's the equation that relates them. I got 2 apples, I can make 1 pie with 2 apples. If I got 4 apples, I can make 2 pies, and so forth. If I have 0.002 strain, that is associated with 58,000 psi. You know what I mean? Like that's all that's happening there, and I just need a way. Because if I had the apples and pies, cool. If I have 2 apples, I must multiply by 0.5. So E for that ratio would be a half. You know what I mean? Or if it's the other way, if I said pies to apples, if I had 2 pies, or let's say I had 1 pie, is equal to 2 apples times, and my constant would be, I kind of missed. Is the constant always the same? Yeah, in that regard, the constant would be a half. Huh. Oh, that's fascinating. Does the constant not change? Yeah, I guess the constant. I need to get my analogy down on that one. Anyway, so let's move on. And but hell yeah. So this modulus elasticity is just the constant that makes the line linear. And make it hit all those points. 0.002 associated with 58,000, if we're talking steel. Okay, so also the strain in the x direction is due to the stress in the y. So that's Poisson's ratio. If I'm tugging on the y, this is going to get reduced in the x. And Poisson's, this v is that ratio, so it's like 0.3. So if, let's just say I'm, let's say that I'm pulling in this direction 58,000 pounds, and we'll just call it 58,000, whatever. We are going to have a stress in this direction due to Poisson's ratio of 0.3. You know what I mean? So the stress in this x direction is going to be a negative value, and the stress in the x direction is going to be negative, and it's going to be this stress in the y times 0.3. So that's this value right there. So we can say the stress in the y, when we have that stress in the y, we are generating a stress in the x direction that's negative, and it's equal to the number for the stress in the y times the ratio 0.3. So 30% of that 58,000 is actually wanting to pull it this way. Cool. Where this V is Poisson's ratio. All right. Of course, the shear stress tau xy produces no normal strains. Okay, that's fascinating. And I almost don't believe that, but whatever. I mean, I guess it produces a change in, like, these lengths don't change. I buy that. And then the angle can change. So let's say we have positive shear. This diamond shape is going to go up into a peakier diamond. And I guess because this length doesn't change, I still... I'll have to look at when we get to a diamond shape. Like, yes, does that mean that any point right here associated with the point over there remain unchanged? So do we have a diamond shape? So if I took the point right here, it doesn't have an associated point over here. But if I went to, like, the point right here, and I go to the point right here, isn't this a reduction doesn't this, like, that's the only thing. I don't get the superposition of shear, because if this is the original change in length, and then I'm at this point, it seems like that crunches in. Because if I took this to the extreme, this box, this diamond shape would kind of collapse in. And so how is that not a reduction in this direction? I guess at a 45-degree angle, it's a reduction in this direction, and it's actually a lengthening in this direction at a 45. So those must perfectly balance and cancel when we're just looking at the x direction. So that's probably what we're going to find, and I'm going to say that was probably a decent explanation and save my brain not to just focus on something. But there you go. So that's one place in the text where it says, hey, shear stresses produce no normal strains. I don't see it right away. That's one that's kind of difficult to see and to be like, why? Or it's okay to say why, and it's okay not to have a perfect answer, and we can move on. And that was one of the ideas this week, was someone's like, when should you start, teaching something? Well, I think right away, and just throw if your channel is going to be full of wrong material, be okay with that. And then, like on my videos, I'll just say, hey, lot wrong, in the title. And I might do that right away and post it, because I know I couldn't get it and there was a lot wrong that I said. Or later I could always change the title to be like, hey, I think a lot's wrong in this. All right, sweet. So, and we're still dealing with plane stress. So we have no sigma z. And so that's not going to cause anything in this. When we're talking triaxial stress, and so now I get that. If we have stresses in 3 directions, we're going to have a pick up another value, and that value is going to be pretty easy. If we have positive z, we're going to shrink in this x direction. So we would have a negative v sigma z. Hell yeah. So it's kind of just, that's cool. So now we're kind of staying one step ahead of the text. And we didn't get very far. I mean, we've just read this first chapter. And what happened was earlier today, I just wanted to, I just opened up the book and I'm like, okay, I see this, don't really get it. Maybe I'll just skip to here. Ooh, twice as much I don't get. Maybe I'll skip to here. And then it's just like, no, I can't. I'm already lost. I don't know where these come from. And so hell yeah. So we just spent quite a bit of time talking about maybe where this equation would come from. So now we see sigma divided by E, because if I got this E to the other side, and in some ways to just really simplify the equation that relates stress and strain, is you have sigma is equal to modulus of elasticity times strain. So you got sigma is equal to EE. So then you can kind of pair these. If I took this E upstairs, I would have sigma is equal to EE, and E epsilon, but you could call this E, who cares? It's the Greek letter E, I would imagine. If it's not, shame on me, but hell yeah. All right, so shear stresses produce no normal strains. This is the resultant strain in the x direction. So we have epsilon x is equal to 1 divided by modulus of elasticity. Or I should say these by, so it's fascinating. Now I'm catching myself, because you could say these by their Greek letters. This could be epsilon x, this could be E, this could be sigma x, this could be V, this could be sigma y. So let's talk about what these values are. Or you could say this is strain in the x is equal to 1 divided by the modulus of elasticity multiplied by the normal stress in the x minus Poisson's ratio for the material multiplied by the normal stress in the y. Hell yeah. So in a similar manner, we can obtain the strains in the y and z directions. And so, cool. So in the... I was just like, how do you do it in the z direction? Well, we don't have any tension. And I still like to refer to this as a force, but we don't have any tension in the z, tension or compression in the z, so therefore we don't have any normal compressive or tensile stresses in the z direction that are causing that big change in length in the z. But because we do have, and for our equations, we do have a positive y sigma we have a positive normal stress in the y and a positive normal stress in the b. Those are going to cause a reduction of area equal to those stresses multiplied by that ratio, Poisson's ratio. And it's going to be a negative. So our strain here is going to be negative sigma x times Poisson's ratio divided by E. And then and same thing here. And so we have the strain is going to be this value for sigma y times Poisson's ratio. It's going to be negative. And you have to divide it by E to get that stress. So that's what we have here. So this was... all right, hell yeah, we ran out of juice, so we have to splice these two together, but hell yeah. So we were talking about how the strain in the Z is just due to the normal stresses in the X and Y, and how they, if they're positive, they're going to suck this face in due to Poisson's ratio. And so that happens with that normal stress times Poisson's ratio divided by E, and that's going to be the strain. So yeah, because this would be the resulting stress on the Z face. If we just wanted the stress on the Z face, you would just have these two terms plus Poisson's ratio times this negative. That would be the stress on the Z face. If we want to know the strain, well, you just divide by E. So that's so at least even in here, this equation, you should see that this is the stress along the Z axis, and then dividing by E is the strain, because stress is equal to strain times E. Bring the E downstairs. That stress along the Z axis divided by the modulus of elasticity is going to give us the strain along the Z axis. All right, let's this one, if we're talking about the strain in the Y, well, hell yeah. The stress in the Y is going to be like, that's going to, like, stress in the Y is proportional to a strain. If we have 58,000 pounds of stress in the Y, we're going to have a strain of 0.002. Cool. And how do we relate stress and strain? Divide by modulus of elasticity. But there's going to be two components in the Y direction, because if we're pulling in this X direction, that's going to suck in this face. And so we're going to have a negative stress equal to the positive X stress times Poisson's ratio. And so we're going to have sigma X times Poisson's, and we're going to subtract that from the Y is trying to pull it, and increase this change in length. Pulling this way is trying to decrease it, but it only decreases at 30%. So there you go. But I'm sure you're going to have problems where sigma X is greater than 30% bigger than sigma Y. And so that's kind of the first relationship that you can maybe, see, is that if that's the case, hey, we're not going to have a net, we're going to have a net negative strain. Even though we might have a positive value for sigma Y, if this thing is 3 times bigger, or more than 3 times bigger, the net strain in the Y direction will be a negative. It'll be, and then so negative strain means that the length decreased. If this was the original length B is our original length in the Y direction. If this length decreases, that change in length is a negative. The original length is B, and our strain is a negative value divided by B. So that gives us the strain, that would give us a negative strain in the Y. Okay, so hell yeah. So now I'm up to speed so far. I get where these three equations come from, and even if that's all I learned tonight, I would be super satisfied and happy. But I think I got 2 more hours in me, so here we go. Probably not. I shouldn't have said that. Probably got 20 more minutes. And I could be just done, you know what I mean? Like, I've done these videos online, and I've just gone through one section at a time. So when does this hellish section end? We go through all the special cases, so it just doesn't end. It's like, we got to get to triaxial stress. I don't think so. So yeah, so I was maybe more right about just another 20 minutes. I mean, just as much as I can take, but we'll see. All right, so we got those 3 equations. And this was enough motivation where if I turned off the camera, maybe I could go through. But I think this next equation is the kicker, because because shear causes rotation of the element, no changes in length of those sides. And yeah, it's probably the more difficult one. Like, strain in general seems trickier than stress, and shear strain is got to be way trickier. You know what I mean? Even just shear stress is trickier than just normal stress. All right, hell yeah. So these equations may be used to find the normal strains. Yep, that's the changes in length in plane stress when the stresses are shown. So if we have a plane stress situation, these equations are legit. But if we have triaxial stress, and that's why these are interesting, why they teach plane stress first when it's like you know, this complicated enough, and then you think this is all there is. But no, I get it. Yeah, you know what I mean? Just adding another term, that's cool. We're going to add that other term later. The shear stress, tau xy, causes a distortion of the element such that each z face becomes a rhombus. And a rhombus must mean that the sides are the same length. That's a rhombus is, I think, similar to what a square would be. It would be a tilted square, be a slanted square, I think. And yeah, because these lengths do not change. The angles change, though. The shear strain, so that's what we're talking about, is gamma xy. Gamma is an angle measured in radians. And so the original block was 90 degrees. And so 90 degrees in radians is pi divided by 2. So this angle now is going to be pi divided by 2 minus gamma xy. So gamma xy has to be the reduction of angle right here. This reduction in angle is going to be equal to the increase in angle. They should have on here, this is pi plus gamma xy. And now I shouldn't call it gamma so much. This is called the shear strain. Shear strain xy. And because shear strain is a rotation of the element, it's this angle is changing, and these arms sweep in a direction, and they're sweeping about the xy plane. So that change in angle is about the xy plane. This side, if you looked at this face, it would still remain a rectangle. It would not become a square with slanted sides, a rhombus. Cool. So the shear strain is the decrease in angle between the x and y faces of the element, and is related to the shear stress by Hooke's law and shear as follows. Same thing with strain. If I remember how we had stress was equal to EE, well, this would probably be a better equation if we kept it in the same. So if we have shear stress is equal to the EE part would be a constant modulus of elasticity, basically, and the strain itself. So just like normal strain, we have stress. Normal stress is equal to a constant times strain. That constant is the modulus of elasticity. Shear stress is equal to a constant, that's this, times the strain. For steel, it's pretty nice, and it actually just comes down to geometry. But this value, the max value, will be a change in radians of 0.004. So it's just double what the max strain for steel is. But this 0.004 is the angle change in radians. So for steel, we have an angle change of 0.004 as a max. That's going to be associated with the max shear strain for steel. That'd be like 29,000 psi. And we have a modulus of elasticity that relates those two numbers. So if we brought this up here, and hell yeah. And when we found E, this was 58,000, this was 0.002, and we divided them. And so then you get the 29,000. But in this is going to be 0.004, and this is going to be 29,000. And we're going to divide that by 4. And so 29 divided by 2 is 15.5. And then divide that by 2. I don't know. I'm just going to... I don't have that one memorized. But... yeah. So, yeah, it must be a smaller number. And maybe I've messed that up too. You know what I mean? Sometimes just the simple algebra, it's easy to mess up. But anyway, so just know that this is a constant. Just know that if we don't put any shear stresses, you know, things that cause this shape to happen, we're not going to get any change in angle. So 0 for this value is going to equal 0 for this value. So that's the equation of a line. If I throw this up here and throw and I should look this up. Damn it. Let's just do it. See how fast we can not do this. All right, I know where these properties are, so there they go. So there's the properties of materials, and we want shear modulus of elasticity, and we want it in KSI, and we want steel. And so yeah, we're 11,000. And yep. And I guess I'm just gonna leave it at that. I thought it would be 15 divided by 2, but it's just a little bit more. So maybe I'm off on my values just a little bit. But yeah, 29,000 is the modulus of elasticity. Well, these are 29 million. 29 million, and this would be 10 million. So modulus, shear modulus is 10 million. All right, so let's go back. Cool. All right. So yeah, I'm not up to speed on this number, and I'm not even up to speed on the max. I don't even know what the actual shear, what would be the max shear stress. So yeah, I thought it was just 29, but yeah, let's go take a look at that number. Might as well. Cool. So we have ultimate shear modulus. Yeah, it doesn't even give you the shear stress. So yeah, that's a bummer. Like you're just supposed to say that the ultimate shear stress for steel is just a proportion of the ultimate normal stress. So that's a bummer that even on these charts they don't just spell it out and give you a value for the max shear stress. Yep. So that's a bummer there. All right, sweet. All right, so let's get back to our little picture. Cool, so we have G is the shear modulus of elasticity. That is the constant that just relates these two numbers. One's really small, one's really big. So this is a really big number. This is in the tens of thousands. This is in the tens of millions. And this is in the 0.00, 4 category. So hell yeah. All right, so note that the normal stress sigma x and sigma y have no effect. So this equation is not related to sigma x or sigma y, have no effect on the shear strain. So consequently, those previous equations in 735 give the strains when so these two equations that we derived, or all three of them. Oh no, it just says these two equations in the x direction, sigma x and the strain. Let's see what it says. Give the strains in plane stress. Yes, because this is a strain equation, And this is a strain equation. Yeah, that's the other thing. It's like, hey, we're talking about strain. This is normal strain, and this is shear strain. Yeah, and so even though there are two different types of strain, yeah, they're both called strain. So consequently, both those strain equations give the strains in plane stress about the xy plane when all stresses are given, or will act simultaneously. So you have sigma x, sigma y, and the strain. So there you go. That was the part that I was kind of curious about a month ago. Is like, yeah, you have kind of a superposition. Like you are pulling in this direction, pulling in this direction. Poisson's ratios collapses the other two proportionally. And then if we do have simultaneously a shear stress along these faces, whether it's positive or negative, this is positive because the diamond shape is all in the first quadrant and it's not squat and sticking out into those other quadrants. That hell yeah, we will have a change in angle of that element. And so, cool. Okay, so now let's see what they do. So it says the first two equations give the strains in the x and y in terms of the stresses. These equations can be solved simultaneously for the stresses in terms of the strains. See, I don't even know. So these two equations, you can solve them. Oh, because you have an x, you have a strain here. See, and I said strain, so I'm at least catching myself. This is a stress. This is the pressure. This is the normal, either it's compressive stress or tensile stress in the x direction. This is what's pulling it apart in the x. Same thing in the y. Is that these two equations have those two values as givens, sigma x, sigma y. So what they're saying is that we can put these two equations together. Yep. And you would then, once you did that, you would have an equation. Well, what would you have? Let's see this. Let's just pretend I solve for sigma x right here in terms of stuff sigma y. I'm going to put that into this equation right here for sigma x, and then I could solve for sigma y as a function of the strain. So this next part must be like, cool, I can find the strain in the y direction solely from the stress in the y. And isn't that right? Isn't that what, I don't know. Let's see what it's actually wanting to do. So the first two equations give the strains in the x and y in terms of the stresses. These equations can be solved simultaneously for the stresses. Oh, yeah, so you can solve for the stresses in terms of the strains. And so let's go back up to these equations. So let's say I just wanted to know the, so if I solved this equation for sigma x, I could throw it into right here. And then I would have an equation relating sigma y and the strain in the y direction. And if I solve this for sigma x, it would also have strain in the x direction. So when I shove it in here, I could get my my sigma y terms together, and then I would have an equation for the strain. The normal compressive or tensile stress in the y direction as a function of the strains. So yeah, so algebraically I could do that. So that's the hardest thing about textbooks is like just in one little sentence and then a little equation, you can kind of lose exactly what they did. And so, and that's a point where you would want to combine these two equations and solve for them. But it's also a good habit just to be able, can you do that mentally? Just any way possible. That's why I said, hey, I could solve for sigma x, get everything to the other side. I would have a strain x and sigma y. I can shove it into here. I would for sure have a sigma y's. I could combine those. And then I could, just get the sigma y by itself, and I would have strain in the x, strain in the y. So that equation will have strain in the x, strain in the y, and that'll be our first one. The other equation they said was to, let's solve this for sigma y, and then we'll have these two terms and shove it in right here. Then I can combine my sigma x terms, and I'll have sigma x as a function of strain x, strain y. And so I'm not going to go through, later I'm going to go through why you get a doubling up of the v squared, and let's see what you get. And so what you get is you get a modulus of elasticity divided by 1 minus Poisson's ratio squared times E, the strain in the x, plus Poisson's ratio again times strain in the y. And so if I knew the strains, both strains, I could know the stresses. And same thing for y. If I knew both strains in the E and the y directions, I could know my stress in the y. Okay, in addition, we have the following equation for shear stress in terms of the shear strain. And this is just rearranged and how I like it. You know what I mean? You have shear stress is equal to, it's relating stress and strain. See how this relates? This is stress, this is strain, and this is a constant that relates them. If you have zero, pressure that's causing the element to shear itself, you're going to have zero change in angle of that element. If you have a max, you're going to have this number. This angle is going to be maxed, and so and this number is going to be big, 10 million. This number is going to be small, 0.004. So then you need a number that relates those, and so that's where we get this value. I'm sorry. This is gonna be like 29. Sorry, this is like 29,000 for the shear stress. This is like 0.004, I thought. And then this is the number about 10 million that relates those. Obviously, 10 million times 0.004 is not quite. And so, so maybe this number is closer to 40,000. And maybe in some books, shear stress for steel can be higher than half. Maybe it can be up to 60%. Cool. All right, but anyway. Yeah, so this is the equation. I mean, this is the way to do it. Because this is y is equal to mx plus b. Except when this is 0, this angle is 0. You know what I mean? So your equation goes through the origin. And as an equation, as a linear equation, y is equal to mx plus b. Your y-intercept term b is 0. And so this value for shear modulus of elasticity is your constant that makes is your slope of that line. All right, equations. So these two equations, these two and this equation, may be used to find the stresses in plane stress when the strains are known. Maybe used to find the stresses. Oh yeah, so there you go. So if I know my strain in the x, strain in the y, and shear strain along the xy plane, which is the change in angle along that it's in the change in angle of the element in the xy plane, making it a diamond shape. If I know those three terms, that's what they're saying, then I can know all principal stresses. Sorry, not principal, just the initial stresses, sigma x, sigma y, and shear xy, and the shear stress. So so let's read that again. These two equations may be used to find the stresses, normal and shear, in plane stress when the strains are known. Cool. Of course, the normal stresses in the z direction is equal to 0 when we're talking about plane stress. Equation 734. Oh, and I guess, I guess you wouldn't call it plane strain because, yes, that was the first thing. I was just like, why aren't they calling this plane strain or something? Why aren't they labeling this strain? Well, it's because if we have plane stress, you get strain in all three directions. So that's significant. Where if you just had plane stress and then a rotated angle, you're not going to get, no, you are. You're going to get a shear in the z direction as well. So yep, and that's why I didn't even finish the Morse. Well, actually, the Morse circle didn't go over that, just barely. Up to this point, it said sure you can also, if you're pulling in this direction, it's kind of like you're just pulling something axially, and then so at a 45 in the z direction, you're going to get a shear. And so your max shear in this might be in the that would indicate a shear in the YZ direction. All right, so let's see where we're at. Okay, so if we know the strains, we can, and that doesn't jive with me just because, it's really difficult to know the strains. Strains are so small, and to know the strains in all directions, in one direction might be particularly small, and then the angle of rotation for the shear strain. Just you would have to have electrical devices to know those, but then you could know the stresses. And I guess that does, because there's part of this chapter that's like, hey, there's an electrical device. Look at this. You know what I mean? So that's why we have this electrical device. And when we put electricity through here, there's going to be a resistance, and this wire is very thin, and we can know the number of the electricity that goes through. When this gets pulled in this direction, it's going to lengthen. And when and we do this at 45s, we're perfect because we can know we can know. I guess we just have enough to know how it pulls in this direction, and also how it diamond shapes if it is going to have some shear. So then, and how we can do those readouts is that we're going to have a change in length. That means that these wires are going to lengthen, because they also Hooke's law says that those wires are going to lengthen. If they lengthen, those wires also reduce in area due to Poisson's ratio. I mean, they lengthen, but then the overall cross-sectional area, we just talked about that, gets smaller, and that smallness will cause an increase in resistance, and that is measurable. So just with a small little electrical device that you can just slap on something and just kind of, just glue it on basically, and then pull on it, hey, there's enough bonds between the glue to actually make sure that this pulls, with the material, and we can measure that. So that is why I'm okay with the fact that they're saying that, sure, if I knew the strains, I could then know the stresses. And so, but that's redundant, because like I said, if you had that gauge, the stresses are proportional to the strains. Oh, no, I guess not. You know what I mean? Well, yeah, there must be a strain Morse circle, because now I'm back to being, halfway confused again. So if I do know these strains from that electrical device, then I know what these stresses are. And then I could go through the whole Morse circle and find what stress is the max, and what stresses are the maxes, what max shear stress and what max normal stresses are going to happen. And then I can design my, and I just don't want those numbers to get bigger than what the material can handle. But in doing so, it's like, what is that saying? Is it saying that these strains can't be bigger? No, I think like this is where, like, I'm almost curious. Like, this is where these equations also are maybe answering a question that I have. Is one of the things with material mechanics is you can drop, you know, like, material can only take so much pressure. Like, that's what we're trying to find, is like, hey, you can only pull on something so much before it breaks. And so we have this idea of, like, hey, if we have this stress high enough, that might be a breaking point for that material. Actually, this isn't going to answer it. So I guess my question is, can these equations, can you have a bigger strain than, can you have a max strain that's greater than, can you have a larger strain that produces a smaller stress from these equations? I guess that's my question. But both are, yeah, like, if you, like, the Titanic is at the bottom of the ocean, and a lot of the things that, a lot of the materials are unharmed. You know what I mean? They don't just, because they're under immense compression, it's every molecule is moving at the same place. Where if you're pulling on a chunk of steel, you definitely will pull it apart. But if you put that chunk of steel, you know, in a vacuum or something, and reduce its, and put a tension pressure on it because of that, it's, or any material for that matter, in a vacuum or under the ocean, it's not going to rip apart at all. So that's kind of yeah, it is fascinating to me. And I don't think this book covers that. Maybe it does, where you have, because that would be like, if you have if you have something in hydrostatic pressure, it's not like you're at a neutral. Like, if you have a material under the ocean that's in hydrostatic pressure, and then you're pulling on it, you're like, well, how much do I get a pull on it? Or pushing on it. That would be a better thing. If I have a bar up on the surface of the earth and I push on it on both sides, or like even just like a chunk of wood or something, I can only put so much compressive stress before it fractures at a 45 due to shear. Put that same chunk of wood at the bottom of the ocean and then push on it. It seems like, I guess, you can push on it the same amount, because the overall hydrostatic pressure changes the locations of the molecules, but doesn't, and that's strain. It's straining the molecules in the X, Y, and Z directions proportionally, and yeah, and that's a neutral state. I would think. So that would be my question kind of going forward. I don't think it's going to get answered in this book at all. I don't think so. All right, so hell yeah. So those two equations can be used to find the stresses, sigma x, sigma y, and tau xy. The shear stress and the normal stresses, when the strains are known. Of course, the normal stress in the z direction is equal to 0. Equations 3.4 through 3.7 are known collectively as Hooke's law for plane stress. They contain 3 material constants: modulus of elasticity, shear modulus, and Poisson's ratio. But only 2 are independent because of this relationship. Okay, so if you, yeah. All right, hell yeah. And the reason this makes an angle, I need to kind of refresh myself on that, is due to geometry. And what happens is, like, when you're putting a shear, let's say you're putting a shear forces on this, this is lengthening. And so you do have a strain in this direction. And I think later on in this book, in this chapter, I think we'll talk about that a little bit. But it's this shear strain that can only lengthen to a maximum. So once this length to that length, if this was 1,000 millimeters, When you strain this length to that length can only increase to 1,002 millimeters. Basically from normal change in length, normal stress. And so, but when that does lengthen, you still are going to have this angle form, and that angle is going to be, that's your max angle. So it is kind of related to geometry. And I think it's why that these are related as well. Don't quote me on that though. But hell yeah, there you go. So you got a relationship between those. So if you know Poisson's ratio, in the back of the book is 0.3, and this is E, then you know that 1.3 is going to go to 2.6, and you have 2.9 divided by 2.6. So that's where you get a value of about 11 million. This is 29 million divided by 2.6. You get about 11 million. I can buy that. But I just don't know what comes. And I thought this value for shear for steel was just half of the normal, and maybe you have to go off half the ultimate, because the ultimate stress. Yeah, let's go there. So what's the ultimate stress for steel? So we have ultimate stress, and we're going to go down to steel, and this is going to be in thousands of psi. And so steel is going to be the ultimate stress for 130,000 psi. So compared to just the yield stress, which can be low as the yield stress is going to be that side. So we could have a yield stress of 75. I was using like 58,000 for, you know what I mean? That's a common number because the modulus of elasticity is 29 million. And if the modulus of elasticity is 29 million, then that means, well, and then typically for steel, you get a strain of 0.002. So just 58,000, 0.002, and 29 million kind of have been used for yield stress. And so I just wish they would have more, values for yield shear stress, but they don't, you know what I mean? So I think just in the book they say shear stress is just going to be half of, but it might be half of ultimate, you know what I mean? So now I need to actually, I don't even know where to go for those. All right. It is kind of a bummer in this book. I do have Hibbler's book, so I might kind of look through that to see what they have going on. All right, so we're down to here. We're going to go through the special cases. So in the special cases of biaxial stress, our shear is 0. Our stress in the y is 0. So here's our equations. Strain in the x, y, z. And then we also have these other two equations that relate stress. And let's see where we could go with this. Okay, so these equations are the same because the effects of normal and shear stresses are independent of each other. Okay, so it already rearranged them. 739. How is this any different than what the ones that they just did? Oh, I see. No, I do not see. So we have strain in the x. That's the same, right? Strain in the x. Yeah, these are unchanged. And these are look to be unchanged. Okay, yeah, hell yeah. So these equations are the same because the effects of normal and shear stresses are independent of each other. I don't get this sentence and then just re-putting up these equations. But anyway, moving on. For uniaxial stress, when sigma y is 0, so that's the part we're getting to. So this is 0, this is 0, this is 0. So these two become the same, and this is becomes that. So I guess I see that. And then this, just if we're trying to relate stress in the x direction to strain, we just use this equation and rearrange. So hell yeah, we're just good to go. Where up here, if we have both these values and we were trying to find the stress in the x as a function of strain, well, we have to find this as a function of the strain, which is, rearrange. We'd have to combine these two equations. So with biaxial stress, or what they're calling that, uniaxial, in the special case of oh, okay, sorry about that. Their pictures kind of got out of order. So here is biaxial stress, where we have stress in the x and y. Normal stresses in the x, normal stresses in the y. These are equations. They're the exact same, except that we don't have any shear stress. So they're all of those equations except this one. Sweet. If we have uniaxial stress, then our sigma y drops out of all of these, and we are left with these equations. You know what I mean? So we talked about these three, and we can find our stress in the x, because that's just a rearranging of this one. It's going to be stress is EE. Okay, now pure shear is where sigma x and sigma y are 0. They don't have a picture of that, and we just have shear. So sigma x is 0, this is 0. Strain in the x is 0. Sigma x is 0, sigma y is 0, this is 0. Same thing for there. So that's another, we talked about how that was one place where I was, I don't know, just a little bit puzzled about, but there's another algebraic way to show that the strains in the x, y, the changes in length in the x, y, and z direction are 0. And our shear term isn't a function of stress anyway, and so our shear term is just looks the same. So our pure shear strain, this is the angle change that forms from this stress, is this equation. In all three of these special cases, the normal stress, sigma z, is equal to 0. Cool, awesome. I'm going to take a little break. All right, hell yeah. So we're back, and we went through those three cases: biaxial, uniaxial, and pure shear. And we saw how these equations, these kind of don't change, except we just drop out the shear. We won't have any shear. And these equations become this. Cool. And let's look at this, though. You know what I mean? So we have strain in the x is just solely due to that x direction. No, yes, this for uniaxial. So yeah, obviously, if we have this, hey, our change in length is so in the x direction is solely due to this normal stress. We are going to get a reduction in the y and z direction, and that's due to Poisson's ratio. Cool. So now we're kind of looking. These equations we've already talked about really don't change, except we just drop out the shear. When we have pure shear, we don't have, and that diagram is not even on here, but if we are in pure shear, just shearing this and trying to make it a diamond shape, we don't have any changes in length in the x, y, and z directions. In all three of these cases, there never develops any normal stress in the z direction. Cool, even due to shear. and even due to, wait, why aren't you picking up normal stress in the z direction due to Poisson's ratio? Like, wouldn't that be the case? Does that kind of slowly start to answer my question? That if we do have plane stress, where we have stresses in the x and y, we are going to have changes in length in the z direction. But why aren't those changes in length in the z direction associated with why isn't it? Why is the change in length in the z direction not associated with a net stress in the z direction due to Poisson's ratio? That I don't get. I swear that kind of popped up in the chapters, and I was under the impression that any material, that kind of slowly answers maybe my question of like, when, like why if you drop something into the bottom of the ocean, it doesn't just break apart due to the pressures. Is that where that comes from? I mean, the fact that I can have a strain, a change in length in this z direction, but not have it associated with any stress. And is it, so here's my other question, is the idea of material mechanics that the stresses are what we're interested in finding the strength of a material? Like if I have this getting sucked in due to Poisson's ratio, but I'm going to say that's not associated with a stress, then I can do that all day long in that direction. This material, in that regard, this material needs to have zero strength in this direction. I mean, it could just be put together with paste. Is that true? Is that true too? You know what I mean? Where you just have like zero. Anyway, I think I'm probably going down a road that I'll regret. So, just regret it into like asking too many questions that you don't have answers to. It's just like, ugh. But yeah, in all three of these cases, the normal stress is in the z direction is 0. Even though you have normal strain in the z direction. Yeah. So normal strain in the z direction is not a function of the stress in the z. Well, I mean, for these are the inputs where we're just saying they're in the xy plane. We're having plane stress, and we are getting strain in the z direction, but that's not associated with a stress. That is fascinating to me. I don't get that, actually. Okay, hell yeah, moving on. So we have volume change. When a solid object undergoes strains, both its dimensions and its volume will change. So maybe this will help explain. I don't think it will, but yeah, we've talked about this. The change in volume can be determined if the normal strains in the three perpendicular directions are known. Well, we just did those equations. Epsilon x, y, and z. To show how this is accomplished, let us again consider the small element of material over here, figure 7.25. The original element is a rectangular parallelepiped having sides of a in the x, b in the y, and a length of c in the z direction. Alright, these lengths a, b, and c in the x, y, and z directions respectively. The strain in the x and y and z produce the changes in dimensions shown, and we've talked about that. This should just say change in length, and the strain associated is for that strain in the x would be change in length divided by a. But we can rearrange for strain is change in length divided by a, and we can rearrange for change in length, which is just strain times a. So that's where they get this value, strain in the x times a. These increases in length are strain in the x times a, strain in the b, strain in the y direction times b, and strain in the z direction times c. The original volume of the element would have been a, b, c, a times b times c. And its final volume is going to be A plus A change, A plus A times the stress in the X. B plus B times the axial strain. Damn it, I'm saying those wrong. Anyway, so we have the strain, which is a stretch, a change in length. The strain in the X direction multiplied by A plus A. B plus B times the strain in the Y axial direction. C plus C times the strain in the Z direction. And as such, this bigger cube has a length of A plus AE, B plus BE, C plus CE, where E is the strain in that axial direction. By referring to equation A, right up here, we can express the final volume of the element in the form of, we have this term, so we factor out the A. What do we do? Yeah, you can factor out an A out of this equation. This equation would be A multiplied by 1 plus strain in the X. We can factor out a B out of this equation, and we can factor out a C out of this equation. Get all those A, B's, and C's to the front, and we can see that that's the original volume. So the final volume is the original volume plus these changes. So this is going to, if our strains are positive, this is going to be an increase in volume. If we have zero strain, there's going to be no increase in volume. Upon expanding the terms on the right side, so if we did factor these out. So anytime they do this in textbooks, hey, we have a very small, we already said this is a tiny number. So we're going to have a tiny number cubed, so that probably goes away. A tiny number squared probably goes away, so we're probably, in the end of the day, what they're getting at is we're probably just going to have 1 plus the strains times the initial volume. And so that's what I see down here. So that's kind of staying one step ahead of the textbooks. I haven't read this at all, but that comes up so much in this material mechanics that just be ready for it, especially with derivatives. And just know that you're dealing with small numbers. It's one of the harder things about material mechanics is that you have to deal with very small numbers and very big numbers at the same time. Because they're basically make up the same equation. Stress, bigger number related to strain. And I got to get better at saying those, because even when I just said stress, I was thinking strain. And yeah, I hate those two terms though, man. They need to change those two terms. No one's going to change them. But that's why I just constantly say stress, PSI, strength is stretch. It's a change in length. Cool. So the preceding equations for V1 are valid for both large and small strains. If we now limit our discussion to structures having only very small strains. So they always have to throw that in there. If you're making a building out of rubber bands, hey, your strains are going to be big. And so you have to use this equation. But for very small strains, it is usually, and that's usually the case, it is to structures having only very small strains. We can disregard the terms in this equation that consist of products of small strains. Any two numbers multiplied together. If you had 0.1 times 0.1, that becomes 0.01. And if you had 0.01 times 0.01, that becomes 0.0001. So if I said that right. And they are compared to this. If this is 0.1 plus 0.1 plus 0.1, you would have 0.3. And if this was 0.1 times 0.1, you would have 0.01. So I would have 0.3. This would be 0.01, 0.01, 0.01. It would be something. It would be 0.33. And then I would just have this term, and that would be 0.01. Times 0.01 is 0.01 times 0.001. So I would have 1 0.3 31. Cool. Instead, I just have 1.3. And that's a huge strain. 10%? Yeah, 10, like 0.1 is a huge strain. That means that's and think of strains as percentages. You know what I mean? It's the percent change in length. If the original length was 1 meter, and I have a strain of 0.1, I just increased that 10%. Now I'm at 10 centimeters increase. All right, hell yeah. Okay, so that is going to be the new volume, is the initial volume times this. So now we have a change in volume is going to be this minus the initial volume. And if we FOIL this in, we'll have a V naught, and then we're going to subtract it by a V naught. And then so we're just going to have these three terms times that initial volume. All right, hell yeah. So the change in volume is this expression. It's the the addition of the strains. This expression can be used for any volume of material, provided the strains are small, we talked about that, and remain constant throughout the volume. Note that the material does not have to follow Hooke's law. Okay. And then furthermore, but it has to remain constant. Yeah, okay, whatever. Furthermore, the expression is not limited to plane stress, but is valid for any stress conditions. As a final note, we should mention that the shear strains produce no change in volume. Okay, so all right, I'm done with that. You know what I mean? There's probably a lot said and no examples, so we just got to move on. But what seemed anyway? Yeah. So you can reread that if you want to. Yeah, because it's just fascinating. I mean, this first one though, the material provided. Note also the material doesn't have to follow Hooke's law. So if one part of it goes if it goes plastic in the X but not in the Y and Z, wouldn't you have like a discontinuity of maybe not. And then furthermore, the expression is not limited to plane stress. All right, and then the shear does not produce any change in volume. So cool. Shear doesn't produce change in volume. Now, I've not gone over that one because it seems like, how is this volume the same? As this shear gets to be large, this thing's just going to collapse in on itself and have zero volume. So with large shear strains, you are going to have a change in volume. So is it just the fact that this equation is based on small strains? And if you have small shear strains, you're going to have... and I get that. I mean, with circles, I mean, if you hardly change these angles, like if this angle just barely changes, I mean, I'm okay with that the change in volume won't have any change in volume. But if you just look at this and take it to the extreme, and this like almost squashes in, and I mean, just squash it in all the way. This length, this thing just becomes 2 times as long, and then there is no more volume. And so, yeah, so that it just feels thrown in there. You know what I mean? Where it's just like, and that's kind of what makes material mechanics difficult, because it's a lot of assumptions. And even in this equation, we've just said the big assumption was that the strains are small. And so I think there should be another sentence here that says that shear strains produce no change in volume if the shear strains are small. Don't you think? I mean, didn't we just prove definitively that shear strains for sure change that rhombus's volume? Interesting. And that stuff can just end you, man. You're just like, I don't know. You know, I mean, how do I put that into my wheelhouse? And because that's the only one sentence explanation that says shear strains produce no change in volume. And it seems like I can prove that they do. Okay, sweet. How much more do we want to do of this? I think we want to get, if we can get all the way through this, I think that would be a good goal, even if we just have to read it. I mean, I want to read it and understand it for sure. And we're still within our goal of 3 hours. You know, this is what I want to do at the coffee shop. And this is about the speed I would have gone at the coffee shop anyway. Probably slower. I don't know how much, and this is a good experiment doing these longer videos. I don't think I'll do them for very much longer just because no one's going to watch them all the way through. They're more for me, and they might be kind of hard on my voice. All right, sweet. So now we're going to move on. The unit volume change. Okay, so now we have this term that's going to be change in volume per volume. I'm satisfied with that because up to this point in material mechanics, we've already said strain is a change in length divided by length. So something that's a change in volume divided by volume seems like a perfect material mechanics quantity to give a letter. So we're going to give this letter a little e. And cool, it's at least not a Greek letter. I can handle that a little bit better. And sweet. And this is going to be known as the dilation. I mean, it seems like they should have called it elation. But anyway. All right, so we have dilation. We have the letter E is defined as the change in volume per the original volume. I can handle that. We already said that. So the change in volume was 1 minus. No. The change in volume was just, we boiled down to the change in volume was the initial volume times the strains, the addition of the strains. So that divided by the original volume is just the addition of the strains. This is the dilation. If I knew the strains in the X, Y, and Z directions, I could just add them together. Cool. By applying this equation to a differential element of volume and then integrating, we can obtain, you lost me, but we're going to apply this equation to a differential element. Oh, okay, I get it. I mean, if we're saying this is the dilation for this tiny, insignificant, infinitesimal element, we can know that change in volume. That's going to be like a dV. Well, from our strain equations, we know strain EY. Yeah, so here's what we'll have. This volume initially is dV. Like it's a little small change in volume. And so is that kind of what they're getting at? Well, let's see where they go with this. By applying this equation to a differential element of volume and then integrating, we obtain the change in volume of a body even when the normal strains vary throughout the body. All right, hell yeah, we got some more juice. And cool, let's do this. I didn't get that sentence at all. So I guess let's read it one more time. By applying this equation to a differential element of volume and then integrating, we can obtain the change in volume of a body even when the normal strains vary throughout the body. The preceding equations, does that mean coming up? For volume, these equations for volume changes, the equation for changing volumes apply to both tensile and compressive strains. Inasmuch as the strains in the X, Y, and Z direction are algebraic quantities, positive for elongation and negative for shortening. Cool. Yep. So yeah. So Anyway. Yeah. So if you have compressive, So right here, here's an equation with compressive or tensile stress. It could be a positive or a negative. And all right, let's see what they say. With this sign convention, positive values for change in V and dilation represent increases in volume, and negative values for E. So there you go. If this is negative, because maybe this is negative, that's going to be shortening. With this sign, yeah. And yeah, so we just said that. With this sign convention, positive values for the change in volume and dilation represent increases in volume, and negative values for change in volume and dilation represent decreases in volume. Let us now return to materials that follow Hooke's law and are subjected only to plane stress. Okay, so we have this figure. In this case, the strains in the x, y, and z direction are given by the equations that we probably earlier talked about. Substituting those relationships into equation 746. So we had an equation. So if we have three different things here: plane stress, stress in the x, stress in the y, and a shear. Let's see how we're going to get those in terms of strain in the x, strain in the y, strain in the z. And so because it's just going to pop out like that, and so this is where you want to go back and be like, does that make sense? Because here's my stress in the x, here's my stress in the y, here's my stress in the z. I'm going to add all the three of these together into that equation, so I can factor the 1 divided by e. I'm going to have a sigma x added to a negative v sigma x. I'm going to have a sigma x minus a negative v sigma x. And so it looks like I'm going to have a sigma x minus 2v. So 1 minus 2v sigma x. Hell yeah, we had sigma x minus 2v sigma x. Cool, so that's where we have this. And it seems like there should be a parenthesis here, but I guess as long as this is all the way the length of that, then you would, these two terms get multiplied. And the opposite is true. If you put something at this level, if this is your like quotient or whatever they call it, fraction, if you put something right at this level, that indicates that you're multiplying it to it. Anyway, so back up here for our sigma z. Holy hell, I'm just saying the wrong things. They get me confused every time. But this strain, this is epsilon y. This is the strain in the y direction. Is going to be equal to, wait, what? All right, so this dilation is stress in the x plus stress in the y plus stress in the z. Okay, yeah. And I think we just found one term and then we double checked it. So if I'm adding all these things up, I'm going to factor out a 1 divided by e again, and then I'm going to, the first thing I'm going to add is this sigma x, and then I'm going to add it to a negative sigma x v, and then I'm going to add it to another negative sigma x v, so I'm going to have sigma x minus 2v sigma x, and then if I add this is going to be a negative v added to a negative v sigma y added to a sigma y. So there we go. So I'm going to have sigma x plus sigma y multiplied by a 1 minus 2 Poisson's ratio v, all divided by e. So hell yeah. So that's where that comes from. So this is where I'm trying to just get better reading textbooks and trying to follow the algebra without, writing too much down. But that would be a good time to, because if you can't see it, I think it would be, yeah, you can put pen to paper to it. That's a good way to do it. But it is good to be able to visualize where the hell they just went from this sentence to here by combining those equations. So we have the dilation, and it's a function of Poisson's ratio, and we can see it's just a function of sigma x and sigma y. The change in volume, the dilation, change in volume per volume, is not a function of the shear stress. And but mainly because we didn't equate it, you know what I mean? Like, the shear stress has to change this way, doesn't it? I mean, physically, did we? It just seems that we just didn't make an equation for that, because in general these strains are pretty small. This change in angle is insignificant. Therefore, this the volume won't change on that thing very much at all. Yep, and that's the only thing. That's the only thing I can restate myself on that. All right, note that this equation also applies to biaxial stress. So if we just have stress in one direction, this drops out, and we're just good to go. Same thing. From this equation, we see that the maximum possible value of Poisson's ratio for common materials is 0.5, because a larger value means that the volume decreases when material is in tension, which is contrary to ordinary physical behavior. Hey, that's pretty good. You know what I mean? Cool. So, yep, this can only be 0.5 because we can't have a negative change in length when we have a positive axial stress. All right, so we have strain energy density, and any term that has energy in it, I think, is really difficult. So we'll see if we can power through this. This might just be see if we can power through and understand it, but yeah, no guarantees. The strain energy density, and what is energy? Energy is force times distance. So it took some sort of force. We're going to have the stress times this area. That would be a force, and this distance could be the change in length. So hell yeah, that might be a good place to start. So we have the strain energy density, U, is the strain energy stored in a unit volume of material. And so this is where you'd want to see the discussion sections 2.7 and 3.9. I should just go right there, but I'm kind of done for tonight. And so let's just do a read through. And because, like, I'm not going there, like, that's the issue with textbooks. If it says, hey, if you're not knowing what's going on, you should go back to these sections. And if you don't do that, there's a chance that you're just going to be reading gibberish from here on. You know what I mean? So that is the bummer about textbooks, is they don't hold your hand, that's for sure. All right, so for an element in plane stress, we can obtain the strain energy density by referring to elements pictured in 725 and 726. Because the normal and shear stresses occur independently, and so yeah, we have the strains, that strain, and then the one that looks like a diamond shape. So this is 725, and this is figure 726. So always go back to the figures, and if you don't have those, already kind of popped in your head. Those are the two figures we're looking at. Because the normal and shear strains occur independently, we can add the strain energies from these two elements independently to obtain the total energy. Let us begin by finding the strain energy associated with the normal strains, that would be this one, since the stress acting on the x face of the element is sigma x. We find that the force acting on the x face, so yeah, hell yeah, anytime you see the word energy, you'd be like, what the hell is energy? It's force times distance. Can you identify a force? Yes, sigma x times this area. Can you identify a distance? Yes, AEX. Cool. So, and then hell yeah. So we find the force acting on the x face of the element. That is equal to sigma x BC. Cool. The area of that face, C times B, times the stress. Of course, as the loads are applied to the structure, this force increases gradually from 0 to its maximum. That's the other thing with springs. If you hardly put any force on, you're not going to get any change in length. Your force is 0, your change in length is 0. As you put a force halfway, that gets it to go halfway, that force is only half as the max. And then once you get to this max, you actually have a max force, and that's what we just calculated. But that is not the force that you actually use to get it from there to there. You put 0, you put sum, you put half, 3/4, and then you put max. So it's always good to go over that, because they're going to throw a divide by 2, and if you don't know where that divide by 2 comes from, or it's the average force that would have been required. It would be the average force required to take this face to there, and that's going to be this max force divided by 2. The max force, because it's a spring, is easy, is the stress on this element, because that stress is holding that force. You know what I mean? If we have a stress on this element, on that face, it's associated with a force, and that's sigma x bc. But that is not the force that took the element from unstressed to that stressed position. So we do half of it. It's the average. Average force times that distance. Of course, as the loads are applied to the structure, this force increases gradually from 0 to its maximum value. At the same time, the x face of the element moves through the distance AEX. Therefore, the work done is going to be the average force times that distance. So here is the force, max. The average is divided by 2. There's that distance. And booyah. All right, provided Hooke's law holds for the material, similarly, the force sigma y, if we have biaxial stress, is going to be that area AC. A is in the x direction, C is the z direction, so we have AC times sigma y. We're going to take half of it. Half is going to be the average force. The distance is going to be, this is B in the y direction. Its change in length is going to be B strain y. And again, the change in length is going to be the change in length. Now, strain is an observation of change in length, and that quantity is going to be change in length divided by the initial length. So if the strain is that change in length divided by the initial length, then the change in length is the strain times that initial length. So that's why we get this strain is going to be the initial length times the strain. This is the change in length. Cool. So the area of this face times the stress on this face is the force. Max force divided by 2 is the average force on this face. Force times distance. This is the distance that force acts on. That's going to be the work in Newton meters. It's force times distance. It's a force times length. That's the units on that. The sum of these two terms. Okay, so now we're going to add them up. We're going to have a half. We're going to have a ABC. ABC. So we have ABC divided by 2, and then the things we don't have in common are sigma x strain x. Sigma x strain x plus sigma y strain y. Hell yeah. The sum of these two terms give the strain energy stored in the element. Thus, the strain energy density, damn it, you know what I mean, they have to go to energy density. Strain energy density is energy per unit volume. Okay, so if this is a volume of that element, and if this is the energy of the element, but this, we see it's a function of the volume. Cool. So if we divide it by the volume, ABC just drops out. So this is the energy per unit volume. And so, and even just right there, I've lost all touch of reality of what this term means, but we'll see if we can gain it back. Thus, the strain energy density, strain energy per unit volume, due to the normal stresses and strains, is, we're going to do this lowercase u1. We didn't actually put any letter on that. So we have lowercase u1 for the strain energy for the, and this is just the normal strains. You know what I mean? This U2 is going to be the shear strains. And then we're going to have to add those two energy per unit volumes together. Probably. Okay, so we get this. The strain energy density associated with shear strains was evaluated previously in section 3.9. See, and I just don't want to go there. That's why we need to go back to chapter 2, chapter 3. And so, bummer on me, and we're not going to do that. But anyway, so I guess, cool. Let's just say if I have shear, it's going to change. Oh, yeah. Shear is going to change distances. It's going to be a force times a distance. A force acting over a distance. Oh, okay, I can buy that. Like, let's say here's your face, and here's going to be your stress, and that means that we have a force in this direction. That force, this used to be just down here, and then we moved up this length. I mean, so this height, if this is a small angle, is just this length times this quantity shear. And then so my force is going to be, and then again, 0 force, 0 change in angle. And so I'm going to take that force, which is this value, which is the shear stress over this surface, and then I'm going to go up this see how we have B, we have this this is the C direction, this is the B direction, so this area is BC. But then this height that we move up is a function of this length A times this this distance. So we're going to have ABC, because we have again we have this this force. So it's fascinating that even though we just did this for stress, I can intuit how you would do this for strain. We're going to have a force that moves this face up. 0 force means it moved up 0 distance. When the max stress is on this, it has a max force associated with it that's holding this distance. But the force to get it to that distance, like the energy, force times distance, is the average of that. So this you're going to take that force divided by 2. So we have C, we have BC times the stress divided by 2 is the average force. The distance is strain times A. And so you get something very similar to this. You're going to get an ABC term, you're going to get a stress term, and you're going to get a strain term. And so it's just like this, except you just have one face. You know, you don't have a sigma x, sigma y. And then that's going to have an ABC. We're going to divide by the volume to get the unit volume. So we're going to have 1/2 shear times strain. Shear force, shear stress times shear strain. Hell yes, that wasn't too bad, even though probably I don't know if you could follow any of that without pictures. But hell yeah. But that's the idea of just reading textbooks. See if you can see how they got from one step to another. All right, now we just add these two together. We're going to factor out the half. We're going to add this, plus this, and that's what we have. So it says, by combining the strain energy densities for the normal and shear strains, we obtain the following formula for strain energy density in plane stress. Cool, we combined, I almost just spaced out, but yeah, we combined those two and we got the strain energy density. And this is for, again, for plane stress. It's when we're given us sigma x, sigma y, and then shear, tau xy. Substituting for the strains from equations 734 and 735. Uh-oh. So now we got to see what they're substituting into this hellish beast. 734. So here you go. Here is the strain in the y, or it's the stress in the y, or it's the stress in the x. So we have a lot going on, but we have, 734 and then 735. So we could substitute any of these things in. We could get rid of, it could be just in terms of stress, because we could cancel out all the strains. So let's see what the hell they do. What are they getting at? So they're trying to get it all in terms of strains. And again, maybe we went back to that picture of that gauge where if we can electrically find the strains, like cool, maybe from that. I don't know, but hell yeah. So what they're wanting to do is substitute these terms, for what they would be in. So in a. Oh, so the first thing we're doing is substituting in. Oh no, they're getting both. Yeah, sorry. So they went from this step to this step. So they were actually able to sub in sigma x, and sigma x was a function of sigma y and a bunch of other things. Sigma or this. Sorry, I'm saying the opposite things again. So this is the strain in the x. This is epsilon x. That equation involves sigma x and sigma y. So when we substitute that in there, we just get more sigma x's and more sigma y's, and probably pick up a Poisson's ratio type thing. And yeah, same thing here. When we substitute this in, we're for sure going to have, and just even think about that. Even right now I'm not thinking, because this strain in the y is associated with the stress in the y. So we're going to have a sigma y plus a sigma x times Poisson's ratio. You know what I mean? So that's that. And it's going to be a minus, because that's going to make it go the other direction. So that's why right here, so that's why I don't even have to go back to that equation, and that's a really good strategy to do also. Get familiar with these enough to be like, hey, this is the strain in the x. It must be due to what's pulling on it in the x. So this equation would be sigma x minus what's pulling on in the y is the opposite. So that's going to be a minus Poisson's ratio times sigma y. And then when we multiply those out, we're going to have a minus Poisson's ratio sigma y times sigma x. So we get one of those terms. Over here, we're going to have the change in length in the y direction is going to be associated with sigma y. So this equation just right here is equal to sigma y minus sigma x Poisson's ratio, and that's it. And when we multiply those two together, we're going to have a sigma y squared minus sigma y sigma x Poisson's. And we just have another one of those. So that's where we get this out of just subbing those two in. So I can see that. That's cool. And here, what are they trying to sub in? They're trying to get rid of this. So let's go back up and see what they have. So they're saying that this is just tau divided by g. That seems like a redundancy, but whatever. And so we just have, this is tau g, and so we're going to have, was it 1/2 tau g? So this must be 1/2 tau divided by g. Is that right? This says shear, or this says this shear strain is just tau divided by g. Oh, so the 1/2 already must be in the equation, and I'm just kind of half losing my mind. Okay, so we have this half, and then if I substituted in this shear strain, this is going to be tau divided by g. So we're going to have tau squared divided by g, and we're going to have half of those. So there you go. So that's done. So we obtain the strain energy density in terms of the stresses alone. You could do the same thing and say that sigma x is what equations? Substituting in 736 and 737. So here's 736 and 737. So sigma, yeah, it gets, we already solved for these. We understood where they came from. It's when you, I guess I don't remember. It's when you wanted to what? You wanted to add these two things. Oh, you wanted to get these just in terms of, I have a sigma x and a sigma y, a sigma x and a sigma y. So I can solve this equation in terms of sigma x, shove it into here, and this will now be a function of sigma y. And then get the sigma y's together, and I'll have sigma y as a function of these two strains. So that's what we have. And so if I have sigma y, I can get this in a function of just two other strains. And so I'm going to see how the strains square, and then we're going to get a Poisson's ratio. I can take this sigma x and get it just in what did I just say up here? Oh, I said I could take sigma y as a function of a couple strains. I can take sigma x as a function of a couple strains. And so they're going to add very similarly. You're going to have this little beast, and this side won't change a whole lot, but we're just saying, hey, we want it in terms of the angle. This is the angle in radians, and this is shear strain, and we want it in terms of that. So shear stress is modulus of shear modulus times shear strain. So this is going to be a g on top times this squared. And that's the more common one that I'm familiar with. You know what I mean? Just like normal stress. Like 58,000 pounds is 29 million times 0.002. So that's normal stress is equal to E times epsilon. Sigma is equal to E epsilon. Normal stress is equal to modulus of elasticity times the strain. And so that's for normal strain. And then if you have shear strain, very similar equation. Shear stress is equal to that constant times that small angle. So a pretty big number in pressure is equal to a constant times a very tiny number in angle. And so that constant must be a pretty decent number, 10 million, 11 million, where the shear stress has to be somewhere in like the 30 million range. Sorry, 30,000. 30,000 is equal to 11 million times 0.004. I just remember that this is, if steel is 0.002, I can assure you from geometry this is 0.004. That is the number that if they're saying strain in steel is 0.002, the angle that forms in shear, the shear strain, is an angle of 0.004 radians, just kind of multiplied by 2. So it's a good way to remember that. All right, so sweet. So now we have these two equations, you know what I mean? I guess we're not going to be doing anything with them because we're just going to get down to here. So that sucks, you know what I mean? But at least we see where they come from, and I can get the energy just as a function of the stresses, or I can get the energy as a function of the strains. To obtain the strain energy, so now we're talking about special cases of biaxial and uniaxial. So if it's uniaxial, this goes away, and this shear goes away. If it's biaxial, this goes away, and I guess maybe this just stuff probably remains. If it's biaxial, all this stuff remains, and this goes away. So cool. So let's to obtain the strain energy densities in the special case of biaxial stress, we simply drop the shear term out of both those. Cool. For the special case of uniaxial stress, we substitute the following values. Okay, so it at least. Oh, so we are just having our stresses in the x direction, so that means we for sure know our strain is just Poisson's ratio times the stress in the x. And then the shear is 0, the shear angle is 0, sigma y is 0, and this is just a function of. I did not realize that. This is just a function of the strain in the x and a strain in the y. This is not a function of the strain in the z direction. And so why is that the case? Yeah, that's fascinating. This whole thing, that caught me off guard. because we're talking about the force times the distance for this axial, you know what I mean? So we solved it for this. Yeah, and I get that. So if we have plane stress, we have a compressive or a tensile here, and a shear. So this, even though we have volume changes and stresses in the z direction, they're not associated with the energy required to do that. The energy is just associated with the max force to get to here, and then divided by 2, because it's going to be the average force to bring that surface that distance. That is the work done. Here it's the same thing, so we have to add that term. And then when we talked about shear, we just talked about that, how this angle changes, and it's very similar. But yes, we will have changes in volume in the z direction, but there's no work associated with those. And that's the other thing from this book that's fascinating. If I have a force in this direction, a change in length in this direction is irrelevant to the energy required. It's force times this distance. You know what I mean? There's no force required to bring that in this distance. Even though it seems like a residual thing or something. But yes, the force required to take this face up to there is going to be the average force times that distance. That's work. There is no force, direct input force moving that in this direction. And that's bizarre that this is an internal element of a thing, because it's just like, is there no internal forces pushing this thing that way? And I guess not, because if there's no internal forces pushing that way, and again, they keep saying that the stresses on this face are 0. So even though you have a strain in this direction, it gets smaller, there's no associated forces or stresses. And I thought, even though I can see that there might not be forces in this direction, I just thought, but this is a stress in this direction, but it's not related. Now my question is it related to, can this face do this all day? If you had a material that could easily, Poisson's ratio is greater than 1. So I pull on it this way, and this stuff just sucks in, and it's a material where if it compresses a certain distance, it's going to fail. The act of this compressing in, doesn't that result in getting closer to failure? That is the one question that I don't have a strong hold on. But it's a good question to ask. But it's just one of those questions I don't know if I can actually ask it myself. But it is good to see what textbooks say and then at least follow along with them. If I'm thinking something contrary to what the textbook says of hey, this is what we see, then that's where I should at least stop pondering so hard on something that could be wrong. Maybe I'll leave it at that. All right, so we're almost there. So we substituted those in, and we have the strain energy in terms of stress or in terms of strain. We have the biaxial case. Oh yeah, and this equation is not a function of the strain in the z direction. So we can easily just sub in this strain in the y, and the strain as a function of the strain in the x. So this is going to be, strain in the x squared minus v, and this term is going to be squared. And so we're going to have Poisson's ratio squared times EX squared. And so let's see what that looks like. And because we have this, everything just cancels out. And because we have, so probably this looks like this, and those squares cancel. But when we do, when we do substitute this into this strain equation, we get this. So we just have the E, we have EX squared, and this divided by 2. This obviously is 0, so all of this cancels all of that. Yep. So I would want to actually do that one on paper algebraically. Same thing up here, got kind of the same thing going on. For uniaxial stress, this is 0, this is 0, this is 0. Well, that's an easier one to see. Hell yeah. But for this one, hell no, this is a little bit difficult. We have strain in the x is still there, and then this value becomes Poisson's squared plus strain in the x squared. And when we have all of that, that's going to cancel. Yeah, because you can't just factor out the strain in the x squared. You would, you have to see this as a factor of a square, and or something like that. But yeah, that's fascinating. Anyway, but that cancels, and you get that term. But there's no example problems for this, so we're just down to the last example. So we have 3 equations. So also for pure shear, sigma x and sigma y are 0, strain is 0, strain in the y is 0. But we do have the stress, so we just have the stress values. So the energy equation just becomes shear squared divided by 2 modulus, shear modulus. Strain energy density is energy per unit volume is going to be the strain modulus times the shear angle, which we call shear strain squared divided by 2. All right, and hell yeah, and that's it. I'm not going to go over any examples. So even going through the energy density, that was lackluster for me because I can see where they're getting these, but now it's just a matter of using them in examples. But I'm done for the evening, and we definitely for sure talked about how energy is force times distance, and with springs particularly, and all materials are linearly elastic with Hooke's law. So you put no force on them, they move no distance. You put a slight force, hell yeah, it moves distance. You could go up to the Empire State Building, push on it, you're moving it. Molecule for molecule, you are moving that building. And so, you know what I mean? So keep that in mind. And then the initial condition for these are that we have some sort of stress in the x, stress in the y, and shear. And so that's going to be related to a force, normal or a shear, and that's going to be your max. And these are already, the whole thing already changed. It went from its unstressed state, and if you put it in this stress state, the volume already changed. We already have strain. And so for the energy, what happens is that we only take half that energy. So the force holding it out here is not the force that was required to bring it from its unstrained state to that stress state. That took half. So the energy is force times distance, and so you have to take the average force times that distance. Now, that's simplifying the calculus, because you have to say, hey, I put a tiny force and I move a tiny distance. That's a quantity of energy. Move another tiny distance, and it took some force to do that. And so you have the area under the curve of a linear line, and so that's how you can take the max force divided by 2. So that's a simplified way to look at it, but still decent, you know what I mean? And it gets rid of the confusion of being like, well, didn't it take the entire force to get this distance to change? No. And the easiest way to see that is because it takes 0 force to move something 0 distance. It took half the force to move it halfway, and the max force is just the force that's holding it there. So anyway, so I got to be done. And but hell yeah, that was pretty sweet. So we tackled something that I didn't think I wanted to tackle, and we tackled the changes in lengths, which is strains of something, and we even talked about shear strains, and did a pretty good job. So all right, thanks for joining me, and that's a video.